everybody. Today we're going to go over the group work from class. Even if there are questions here that your group didn't work on, this might be helpful to you to see more examples of proofs and to pause the video and to see if you can do them yourself before I go through the answers. So here we have isosceles triangle ABC. So the whole triangle is isosceles, so I know it has two congruent sides. They also tell me that CA is congruent to CB. Oh, I already put that in. And that CD is the altitude to AB. If CD is the altitude to AB, that means it's perpendicular to AB, which means it forms right angles. So I almost have enough information here to prove the two triangles congruent. Let's see what else I can get here. So there are two options from what I see. We have two right triangles, and we know that the hypotenuses are congruent. And I also see a shared side because of the reflexive property that we can say is congruent to itself. So I see that these two triangles can be congruent by hypotenuse leg, hypotenuses and a pair of legs. Or definitely you could see that since it's an isosceles triangle and it has two congruent sides, it also has two congruent angles. And then you would get the two triangles are congruent by AAS. You can go with whichever one. If you were working on this one in class and you had the fill in the blank proof, it led you towards using hypotenuse leg. So that's the one that I will go with here. So let me make my statement reason sure. Okay. One is our givens. To save some time in this video, I'm not going to write all the givens down, but you definitely should write them down when you are working on a test or a homework assignment. We said after our givens that we had two right angles. So I'm going to write angle CBA and angle CDB are right angles, and that's because perpendicular lines form right angles. We have an altitude. It's a perpendicular line that forms a right angle. You could also write as your reason altitudes are perpendicular lines that form right angles. That's a little bit more specific to this question, so I'll add that in. Altitudes are perpendicular lines that form right angles. After that, since I know that we're going to be using HL, based on our information here, I actually have to make the statement that the two triangles, CDA and CDB, are right triangles. And my reason for that is going to be a triangle with a right angle is a right triangle. Okay, so far from our givens, we have that we have right triangles. We drew that conclusion in step 3. And we also have the congruent hypothesis that was part of our givens. So all we need to do next is mention the legs, which is the shared side between the two triangles. So let me continue over here and mention that. So I'm going to write CD is congruent to itself. That's by the reflexive property. And then finally, we now have included all of our information to make the statement that triangles are congruent to each other by HL. Remember, whenever you plan to use HL, you actually do have to make the statement in your proof that the two triangles are right triangles. Okay, here is the second question that was given out to people in class. So we know that ED is perpendicular to DA, so they form right angles. We know that BA is perpendicular to DA, so they form right angles. I know that DC right here is congruent to AF, and I know that angle E is congruent to angle B. So taking a look at what we have here, we have the blue angles and the purple angles. But notice how my congruence mark is on DC here on this triangle and on AF of this triangle. DC is not the whole side of triangle DEF. The whole side would be DF, from D all the way down to F. And notice how AF is not the whole side of triangle ABC. The whole side would be AC, from A all the way to C. So the information that we have here is not about the whole side. And we need the whole side being congruent to the other whole side in order to use it to prove the triangle's congruent. Notice if I wanted to make DC bigger, to make it go all the way down to F, I would have to add on CF to make DC extend all the way to F. And notice if I have AF and I want to make it bigger, I want to make A go all the way to C, I also need to add on CF to make A go all the way to C. So I'm going to be using the addition postulate here, and to DC and to AF, I'm going to be adding the same segment CF. So in my proof, I'm going to have to make the statement that CF is congruent to itself if I'm going to be adding it to both segments. Remember, when you're using addition, not only do you have to start with congruent segments, but you also have to be adding congruent segments. So we actually do have to make that statement in our proof. Once we do that, we'll use addition to get information about the full sides DF and AC. And then we'll have the triangles congruent by angle, angle, side, angle, angle, side. So we have our plan. Let's get going. So let me make or on a homework assignment. So let me mention the conclusions that we drew. So first, we have the perpendicular lines. So we mentioned the right angles. So that's angle EBF and angle BAC or BAF are right angles. And for my reason, I'm going to write perpendicular lines form right angles. That's how we knew we had right angles. We had perpendicular lines. Okay. Um, since I'm going to be using that pair of congruent angles for angle, angle, side, I actually do have to and make that those angles are congruent to each other. We know that any two right angles are congruent because all right angles are congruent. From there, we know that DC is congruent to AF. That's part of our givens. And we know that angle E is congruent to angle B. That's part of our givens. Once again, you need to write down your givens when you're writing a proof. I'm just not doing it here to save time in the video, so it's not like 3 hours long. We talked about how to get the side that we need, which is DF and AC. We needed to use addition. So let me show you what that addition would look like in my proof. So I'm going to be starting with DC on the side and AF on the side. And to each one, we said that we were going to be adding CF to get the full side of each triangle. But wait, in order to use addition, we need to be starting with two congruent segments. DC is congruent to AF, that was given to us. But we also need to be adding two congruent segments. And they didn't tell us that CF was congruent to CF, and we didn't write that in the proof. So we actually do have to add in a step in between 3 and 4 here. So let me just make it step 3.5. And I'm going to indicate that it comes in between 3 and 4. And in step 3.5, I'm going to make the statement that CF is congruent to itself. And the reason for step 3.5 would be the reflexive property. So just note that the reflexive property statement needs to come before the addition in order for the addition to work, because you have to be adding two congruent segments. Sorry about that. Okay. Now let's take a look at what our addition gives us. So if I start with DC, oops, let me go to my diagram. So if I start with DC and I add on CF to it, I get the whole side of that triangle DF, which actually was the whole of our addition. And if I start with AF and I add on CF, I get the whole side of that triangle AC, which was the goal of the addition. This step is by substitution. Remember that always follows either addition or subtraction. And all we did from step 4 to 5 is replace the addition with what it was and replace this addition with what it was. So that's why it's substitution as well. Okay. Now we have all the information necessary to prove the two triangles congruent. So we could finish off this proof by saying triangle ABC is congruent to triangle DEF. And we proved this through AAS, angle, angle, side, angle, angle, side. Next proof. So here we know that FA is perpendicular to AD, and we know ED is perpendicular to AD. Why did I use different colors for those? Let me use the same color. And we have that AC is congruent to DB. So here's AC, and here's DB. And I also know that angle F is congruent to angle E. So already I see that we have two congruent pairs of angles, the green angles that we were given and the purple right angles that came from knowing that we have perpendicular lines. It would be really great if we had side AB of this triangle on the left and side DC of this triangle on the right. We would be all done then. We would have angle, angle, side, angle, angle, side. But unfortunately, we don't have side AB and side DC. If you take a look, we have information about AC, which is longer than AB, longer than the side of the triangle. And over here, we have DB, which is longer than DC. It's longer than this side of the triangle. So in order to make the information smaller and get the sides of the triangle that we need being congruent to each other so we can prove the triangle's congruent, we're going to need to use subtraction. From AC, we're going to need to get rid of BC, and that will leave us over with AB, which is the side of the triangle that we need. From DB, we're also going to have to get rid of CB, and that will leave us over with DC, which is the side of the triangle that we need. So in order to use our subtraction, since we need to be starting with two congruent segments and subtracting off two congruent segments, we are going to have to make the statement that BC or CB is congruent to itself. That way we can subtract it from both AC and DB. So that's got to come in our proof before our subtraction. So let me start here. Once again, I'm going to let you all day, but you definitely should when you're writing a proof. You need to. That's your starting point. I'm going to mention right angles because that's the conclusion that we drew from having the perpendicular line. So that's angle A and angle D are right angles. And the reason for that is that perpendicular lines form right angles. We talked about before we can do the subtraction to get sides AB and DC that we need to make the statement that BC is congruent to itself because that's what we're going to be subtracting from both of those long segments. So let's do that as our next step. I'm going to make the statement that BC is congruent to itself. That's the reflective property, reflective of an X. And finally, after that, we're ready to do our subtraction. So for our subtraction, we're going to be starting with AC on the side. And we're going to be starting with DB on the side. And we talked about how from each one, we're going to be subtracting BC. So we just get the sides of each triangle that we need. Let's just verify quickly it works. Are we starting with congruent segments? Yes. Are giving us that AC and DB were congruent? Are we subtracting two congruent segments? Yes, because in step 3, we made the statement that BC was congruent to itself by the reflexive property. So this is the subtraction postulate. So I'm just going to write here subtraction. And let's go to our next step after that. If we take AC and subtract off BC, we're left with AB, which is the side of the triangle that we were interested in. And if we take DB and subtract off BC, we're left over with DC, which is the side of the other triangle that we were interested in. That substitution, we're replacing the subtraction with what it is. And remember, subtraction always follows addition or subtraction. Okay, now we have all the information that we need for angle, angle, side, angle, angle, side. So we can make the statement that the two triangles are congruent to each other by angle, angle, side. Okay, let's move along. Here is the fourth question. So here we have AB is perpendicular to BC. We have DE is perpendicular to EF. We have BC is parallel to FE. And we have that AB is congruent to DE. And we're proving the triangle's congruent. So anytime that we have parallel lines, I'm just going to highlight them. And I'm going to look out for a transversal that intersects them. So I see a transversal here. So already I see a Z letter. And in the corner of my Z, remember I have congruent alternate interior angles. So I see already I have two pairs of angles followed by a congruent pair of sides, angle, angle, side, angle, angle, side. I saw a bunch of people trying to use the addition postulate in order to get side AC of that top triangle and side DF of this bottom triangle. Notice that you can't do that because you don't know that AF and DC are congruent to each other. So you won't be starting with congruent, even if you are adding congruent to it. So just verify you have the right information before you try to use addition or subtraction. I'm not going to write this whole proof out. We have a plan. We wrote out a bunch of proofs already in this video. So what you need to include in your proof is your givens. Then you need to include that you have right angles. The reason for that is that perpendicular lines form right angles. You need to also say that the two right angles are congruent to each other because all right angles are congruent. Then you need to make sure that you mention your alternate interior angles. So you can say angle BCA is congruent to angle EFD. And your reason would be alternate interior angles are congruent when lines are parallel. The when lines are parallel part is very important. You only know alternate interior angles are congruent when lines are parallel. If they're not parallel, you don't know that for sure. Then you can say the two triangles are congruent by angle, angle, side, angle, angle, side. I want to briefly talk about the two challenge questions. So each group had different challenge questions. So if you had this challenge question and you got up to it, your information was that AB is parallel to DC and that AD is parallel to BC. So notice that you have two pairs of congruent alternate interior angles here. So already we have two pairs of congruent angles. And we have a shared side between the two triangles. It's congruent to itself by the reflexive property. So we have angle, side, angle, angle, side, angle. So when you're writing your proof, you need to mention your givens. You can put that as step 1. Then you need to mention that angle ABD is congruent to angle CDB. And also that angle ABD, the red one, is congruent to angle CDB, the other red one. And that angle ADB, this green one, is congruent to angle CBD, this other green one. Your reason for both of those statements can be alternate interior angles are congruent when lines are parallel. And then you need to make the statement that DB is congruent to itself. That's by the reflexive property. And then you can say the two triangles are congruent by ASA. ASA. This question over here was a little bit more complicated. We're told that AB is congruent to AC. We're told that AM is congruent to AN. And we're told that angle BAN, so BAN from here to here, is congruent to angle CAM from here to here. Our goal is to prove ABM, so this triangle, the small one to the left, the small narrow one to the left, is congruent to ACN, so the small narrow one to the right. So notice how this red angle is not inside that small left triangle, it's too big. And this green angle is not inside the small triangle on the right, it's too big. So in order to make it smaller, you could subtract the shared part of the angle. So that would be angle MAN. You can subtract it from both angle BAN and angle CAM. So once again, you can subtract the black shared part of the angles from both the red angle and the green angle in order to be left over with just the angles that you need in each of those two small triangles. Then you would have SAS, SAS. If you choose to do this one and want me to check over your subtraction postulate, all you have to do is email me a picture, and that totally works.